Hi, welcome to all my viewers. In this session, I will demonstrate the fourth experiment in Power Systems Simulation Laboratory regarding load flow analysis using Newton-Raphson method in MATLAB. On to the left side of your observation pad, first take down the question. Problem on load flow analysis. So, for a sample system which contains 4 buses, obtain load flow analysis using Newton-Raphson method. Treat base MVA of the system as 100 MVA and acceleration factor as 1.6. So sometimes they may give you acceleration factor as 1.6 to get confused, but however, in Newton-Raphson method, there is no need for acceleration factor. Bus data of the system. So it consists of 4 buses, of which the first one is slack bus and the remaining 3 buses are PQ buses. So the bus number 1 consists of voltage profile of 1.04 at an angle 0, whereas the second bus is a PQ bus having a real power demand of 50 megawatts and reactive power demand of minus 20 MVAR. Similarly, the third bus is a PQ bus having minus 100 megawatt of real power demand and plus 50 MVAR of reactive power demand. The fourth bus, the last bus is the fourth bus, which is having 30 megawatt of real power demand and minus 10 MVAR of reactive power demand. And the remaining data regarding the line data, it consists of 4 buses. So the sending end is 1, receiving end is 2. At that moment, the element having resistance of 0.05 plus reactance of 0.15. Next, similarly, in between 1 and 3, zero point 0.1 as resistance and 0.3 as reactance. In between 3 and 4 buses, resistance is 0.05 and reactance is 0.15. Next, in between bus 2 and bus 4, resistance is 0.1 and reactance is 0.3. In between bus number 2 and 3, resistance is 0.15 and reactance is 0.45. Okay, so this is the bus data as well as line data of the system that is given in the question having a base MVA of 100 MVA. So now obtain the solution using Newton-Raphson method on the left side part of your observation pad. On to the right side, write down your title of experiment, page number, date, etc. Experiment number, date, etc. Write down the aim to obtain load flow studies using Newton-Raphson method for the given system and to verify the same using MATLAB. Apparatus required, personal computer with MATLAB software. And before going to see the program and output, first I will explain you the commands. As I said in the earlier experiment, we are going to declare 2 variables. One is bus data and other is line data. So bus data matrix consists of 4 columns, in which first column represents serial number or bus number, second column represents bus code, that is 1 for slack bus, 2 for PV bus and 3 for PQ bus. Third column represents voltage magnitude and voltage angle is represented in fourth column. Fifth and sixth column represents real power and reactive power demands in megawatt and MVAR respectively. Seventh and eighth column represents real power generation in megawatt and reactive power generation in MVAR respectively. Ninth and tenth column represents the limit of your reactive power in MVAR, that is ninth column represent minimum limit and 10th column represent maximum limit of reactive power in MVAR. Last one, 11th column represents reactive power injection in MVAR. So this gives you bus data matrix and one more variable called line data matrix. So line data matrix, as we have seen in the first and second experiment, it consists of only 4 columns, but in your third Gauss-Seidel experiment as well as Newton-Raphson experiment, the same line data matrix consists of 6 columns, but however the first 4 columns remain same as we have seen in the first and second experiments. That is, of 6 columns, the first column represents sending end, second column represents receiving end, third column represents resistance between sending end and receiving end, fourth column represents reactance between sending end and receiving end, fifth column represents half of the susceptance value, and sixth column represents line setting or transformer tap setting. That is, if there is any transformer in between those two buses, that is in between sending end and receiving end, then the transformer tap setting value is inserted in the sixth column. Otherwise, if there is no transformer, it is treated as a line, then the value inserted in the sixth column must be 1. And at last, you have to type these four commands. One is lf bus, second is lf Newton, third is bus out, and fourth one is line flow. Since lf bus is the command, use it to obtain admittance matrix using, use it to calculate admittance matrix. Next, lf Newton is the command, use it to obtain power flow solution using Newton-Raphson method in MATLAB. Third command, bus out. Bus out is the command used to print the complete information about the buses. And lastly, line flow is the command used to print the line flow and line losses. Okay. So these are the various commands that are to be written in the program. Okay. Lastly, I shall explain you the program. Okay, see this is the program. The first two statements, CLC and clear all. CLC is the command to clear the command window, and clear all is the command used to clear workspace and history. So given that base MVA of the system as 100, so writing down base MVA equal to 100, and they have also given acceleration factor as 1.6, so declaring one more variable called acceleration equal to 1.6, and I am taking my accuracy as 0.00001, so accuracy equal to 0.00001, and maximum number of iterations I am specifying it as 50, so declaring one more variable called max iter is equals to 50. So from the given system data, the first bus data matrix consists of 11 columns. So see this bus data matrix, of which the first column represents serial number or bus number, second column bus code, third column voltage magnitude, and fourth column voltage angle. Fifth and sixth columns represent reactive power, active and reactive power demand in megawatt and MVAR respectively. Similarly, seventh and eighth columns represents real and reactive power demand in megawatt, real and reactive power generation in megawatt and MVAR. Ninth and tenth column represents a reactive power injection, that is minimum and maximum reactive power limits, as they do not specify, taking it as 0, and also reactive power injection, last column, they do not specify, so taking it as 0. And you know the way to write your line data matrix. First column represents sending end, second column receiving end, third column resistance, fourth column reactance, fifth column susceptance, as they do not give any, taking it as 0, and last column represent transformer tap setting, since there is no transformer, treating it as line. So for line, the entire sixth column is treated as 1, and at last typing all those four commands. Okay, now I will solve this, or I will explain you by copying this program in MATLAB and running it. Okay, so open MATLAB, set your current directory, and then go to file, choose blank M file, then type down your program. Okay, so this is the program. I have typed it, instead of typing I have made a copy paste. Okay, so this is the program. Now this is the button or green color arrow mark to run. If you save, it will run. Otherwise, first, even though you press run, it will ask you to save, and then it will be run automatically since you have pressed. So now I am pressing it. Since I did not save it, it is asking me to save. I am saving it as exp4 since it is fourth experiment. So it is getting automatically saved and run. So in the command window, now you can see the result. Okay, so this is your result. So see, power flow solution by Newton-Raphson method. It is the solution is obtained in 4 iterations only, and this is the bus voltages magnitude and bus voltages angles, real power load demand, real power generation, reactive power load demand, reactive power generation, injected MVR, everything. Okay. Similarly, line flow and line losses. So the total losses is only 4.042 megawatts and 12.127 MVAR only for line losses. Okay. So that is the way how to do it in your MATLAB. After doing in the MATLAB, you have to make a cross check whether the theoretical solution is getting matched with the obtained practical solution or not. If it is perfect, then you have solved your complete solution in a perfect manner. Otherwise, you have to make a cross check with your theoretical, since the practical will not give any problem. Otherwise, you have to check the input whether you have given a correct input or not. And finally, once the theoretical solution and practical solutions were matched, then write down the result at the end. The load flow analysis for the given system using Newton-Raphson method is obtained theoretically, and the same is verified practically by using MATLAB software. Okay. Thank you viewers for watching this experiment in YouTube channel. If you like the demonstration, please press like and give a comment. At last, don't forget to subscribe to my channel. For more updates, stay tuned in my channel at YouTube. Thank you.